Okay, I think we're all good.
Okay. Hi guys, this is Naga. I'll be continuing some topics from the last week. Last week we discussed about continuous consistent hashing and like how to relieve the hotspots. And there were a couple of topics which I wanted to cover, and we pushed it to this week. And they were actually on like sloppy quorums and anti-entropy. Before we get into that, like today I wanted to talk about all replication methods. So let me share my screen just to give you an idea what I'm going to cover. Then I'll switch to the whiteboard. So today I'll briefly cover all the replication methods like single leader replication, multi-leader, and there is a leaderless replication. So that's where like we get these topics of sloppy quorums and anti-entropy of using Merkle trees. So before we go there, like I'll be covering all this, like what single leader replication is, like how do we set up a new follower, what happens if a leader fails, and similarly what are the advantages of multi-leader, and what are the databases that we have, and and how we do leaderless application, what are its advantages over the leader-based or multi-leader applications. So let me switch I'll stop sharing and I'll switch.
No, don't stop sharing. Yeah.
I don't know if I can switch this to camera without that.
You just need to on your camera, that's it. Yeah.
And then.
And you stop sharing then.
Okay.
Okay. And the audience can pin you so they can see you all the time.
Okay, okay, got it.
So that's what I'm going to pin Naga. So if other people are speaking, still I should be able to see only Naga.
Okay, got it. So I just turned it. So we have, I hope everyone can see the whiteboard.
Yeah.
I wrote replication, single leader, multi-leader, leaderless. So before stepping into what each of this is, I'll just briefly tell like what replication is and why it's important. So like in system design interviews, it's a very common question that like you're asked always to scale to billions of users, or like your system should always have higher availability, and those are like always one of the key requirements that you need to fulfill. So one of the methods, you make sure that your system is available always, and is by ensuring that you make multiple copies of your data, and like you make sure that you always have some server of the customer request. So the method to do that is replication. Like we replicate the servers as multiple copies, so that at least we have some copies always ready to serve the customers. So that's the idea of replication. And sharding is like, even if you do sharding, where that's another concept which we briefly covered in the last meeting. So along with sharding, you obviously need to have replication. Without replication, the systems are not highly available. That's this is like one of the key concepts that you need to understand, if not already. So with that told, like there are three types of replication, like how you can set up a replication in your server environment or your system. So one of the method which many databases follow is a single leader replication. So the concept of single leader is like you have only one leader, and you have many replicas, like you can say this is replica 1 and replica 2, and you can have as many as you want, as your system needs. So the concept of leader is that like when the client is making requests, so all the rights will only go to the leader. So all the rights normally go only to the leader. But if he wants to read any data, he can still go to the leader, or it can go to any of the replicas. We can make read requests to any of the replicas. This is the general idea of the single leader replication. That like leader is clients always write to the leader, and for reading any data, they can reach out to any of the replicas. So, and it's the leader's responsibility to make sure that all the replicas are aligned. I mean, like all the replicas have the same copy of data. So, and in this single leader replication, so there are like certain strategies on which you can make sure that like the replicas are replicated. So one of the mechanism is like whenever client writes to a leader, it can synchronously update all the replicas. So this is one of the strategy. So when the client writes to a leader, if there are two replicas, it writes before sending the response to the client, like a success response. It actually writes to all the replicas, and if all these replicas acknowledge to the leader that they have completed the write, then only the leader will respond to the client that write is succeeded. So this type of mechanism is called as synchronous replication. In a single leader, you can have synchronous. Let me write it here. One of the strategies is synchronous, which we talked about now. And other is semi-synchronous. I'll tell you what this is about. And other strategy is asynchronous. So these are the strategies on which like the leader and replicas are like synced. So we talked about synchronous. As we know, like each write, it makes sure that all the replicas have that copy of data, and then it responds to the client. So what is the advantage of this synchronous application? We always have consistent copy of data. I mean, like any replica, like later if client wants to read any replica, he doesn't get any stale copies of data. So he always gets, I mean, like the client always gets up-to-date information. Like this is like kind of strongly consistent kind of system from the database perspective. And let's take about and the advantages. As you know, like for each write to complete, it's going to take a lot of time. The latency is going to be very high in this case, because if the normal write takes like 200 milliseconds on a single leader, and if it takes like at least another 200 here, another 200 here, so by the time it responds to the client, it will be like 600 millisecond response. So that's one of the drawback of synchronous method of replication. So that's why most of them don't use this synchronous, because it's very costly, and the client normally doesn't wait for longer, right? So the another one of the good in between concept is like semi-synchronous. So here the concept is like if you have many replicas, let's say replica 3 also. So here you only let's say like leader will make sure that only one other system at least will have up-to-date information just like a leader. In this case, let's say replica 1, I'll always make sure that I will update synchronously. Whenever I get any write, I only write to replica 1 and I'll respond to the client. So in this case, it's kind of if each request takes 200 milliseconds, in this case, it will respond within 400 milliseconds. We have another 2 replicas. So these 2 will happen asynchronously. That means that after responding to this, there will be like these two replicas will get the data asynchronously from the leader and update it. That means that in that time, like when it is yet to be updated asynchronously, client by chance if he gets redirected to replica 2 or replica 3, he will read the stale data. That means that if some client has written up recent data on leader and it's available in replica 1, but if client connects to replica 2 or 3 before it's getting synced to a sync mechanism, so he will read the stale data. So that's one of the disadvantage. But the advantage is that it actually responds within quickly, but still ensuring that the data is available in one other system apart from leader. And the other approach is asynchronous. In this case, it doesn't only leader will actually acknowledge the write directly. Let's say in this case 200 milliseconds. So all of the replicas will get the data from leader and update the systems asynchronously. So which means that the latency is quicker. So the write requests are served much faster. And I mean, like in the case, like writes are processed very fast. It can process many writes, but like the reads can still get stale data because they all are processed asynchronously. So any doubts before we move on to another concept?
Naga, can you please explain semi-synchronous in just a gist?
Okay. Yeah. So the synchronous, you all know, right? Replica 1, 2, 3. Like leader, before acknowledging the write from the client, it makes sure that all the replicas, like replica 1, 2, 3, are updated synchronously. That means that leader waits from the acknowledgement of 1, 2, 3. Like if these are the number of replicas available in synchronous mechanism, it's going to wait for all of these replicas success acknowledgement before responding its own success acknowledgement to the client. In a semi-synchronous, so the idea is we need not update all of the replicas to make sure that they all have the latest data. Let's make sure that this is the idea of replication is that you have data not just in one single system, but at least another copy, just to make sure that if as a leader, if I am powered off or if I am out or like if I go outage unknown reason or if I fail, I have at least one more system which has the latest data as me. So in a semi-synchronous, you can still achieve that. So let's say in this case, replica 1, I want to do synchronously. So the client is writing to the leader and leader only makes sure that it synchronously writes to replica 1, but not replica 2 or 3. So it just waits for this replica 1 response. And as soon as replica 1 response is received, it sends a success acknowledgement. If one request takes like, if leader takes 200 milliseconds, replica takes 200, it will respond within 400 in a semi-synchronous. But in a synchronous, this will be like 600 plus 200, it will become like 800 milliseconds. If you take an analogy of like how, when you are going to respond. And in asynchronous, it's going to respond within 200 milliseconds. But there are advantages and disadvantages in each approach, right? In semi-synchronous, you are at least ensuring that apart from the leader, you have at least one more copy, latest up-to-date copy written by the client. If even in case of failures, you are sure that data is in some other node available. But in asynchronous mechanism, if leader fails, and if this data is not yet replicated to the replicas in async mode, then the latest data is lost if you go for async. In asynchronous, it's so performance intensive. Like for each write, you are spending so much time just to make sure that you have strongly consistent, like all replicas are up to date. So you cannot serve many requests in synchronous mechanism. In semi-synchronous, it's kind of between both. So you have the true idea of replication, at least making sure that one other node has the up-to-date copy, but other nodes can go in async fashion. But in asynchronous, you have the advantages is that it's very highly available compared to other two approaches, but there are chances that you read stale data. So these are some of the trade-offs which you can discuss. Yeah.
So if the leader dies, do we have any algorithm to select any other leader? I mean, which of the replica will be the leader?
Yeah,
do we have any algorithm or?
I'm about to get into that, like how this replication works and what if the leader fails.
Okay, sure, pardon.
So before going to that, any doubt on these three strategies? Okay, I assume no. So let's get into the next topic. So let's see like how the replication works actually. So let's understand that. How the replication works. Actually touched about this in some of the other my in-person meetups, I think. But the general, there are like several ways on how we can make the replication work. So one of the strategies is like the leader, whenever it accepts the writes and it puts like in this database or something, it internally has some concept of write ahead log. It's just append only sequence of log, and it's called like write ahead log, WAL. So this write ahead log concept is that all databases also have this in, I mean like, but it's called in some databases as bin log like MySQL. In some other databases it's called write ahead, and I mean like it's just called in some other terms, but this log is available in all of the databases if you just observe. So the concept of this is before writing a data to the database or your permanent disk storage, you also where the true data exists in the form of tabular format, like you write before like in a this is again a persistent log, like a write ahead log. So it just appends the data here, and then it just processes the order. I mean, like it can just respond the right success acknowledgement. So the concept of this write ahead log is that this is still a file, kind of which is still accessible in much efficient manner than the actual original disk place where you are actually going to store the data. So this log will actually, whenever the write comes, the leader writes to this write ahead log, and then it responds to the client as success. So this is to ensure that it's durable. So after writing to the write ahead log, it actually fulfills its row update request, or like insert, update, or delete, or whatever it is. So what replicas can actually do is they can actually take a access to this write ahead log, or this leader can actually ship this write ahead log to all the replicas so that they can process the data in the same manner. So this log, you can imagine like some sequence of like depending on the write 1 or write 2 or write 3 from the clients in some form. You can imagine this write like SQL statement, or you can as a row value data, or like if it's a trigger, you can also take this as a trigger. Whatever the statements that the leader in the form of write he's getting, the same, like whether it's a SQL query or like the insert or update query, or it can also ship the row data which is updated. So whichever the row is updated, it can just send the whole row data instead of just one column. So the client is writing just one of the column, the leader can ship the whole new row data to all of the replicas, so that they just replace that new row in their own base. So these are just like one of the strategies. Like you can either pass SQL insert or update queries as is received from the client, or raw data or trigger, like in the form of this write ahead log, which can contain all of this. And then like each of the replicas can take that and process that same log, and then like get to the same level of leader, whatever the state it is. Any questions here before I move on?
So hi Naga, I have a question here.
Mm-hmm.
So is the write ahead log, is it a file on the file system, or is it part of database, or where does it live?
It's not part of the database, but it's some durable storage. Even if leader crashes, this log is actually available when it restarts. First thing it actually does is, so the idea of write ahead log is before processing the write to the database, the leader writes to this write ahead log. And let's say if I have some one query, two query, which is yet to be processed, there are two statements which are yet to be processed, but it has acknowledged the client that it wrote, because it wrote to this write ahead log, but it has not yet returned to the database, so it's sitting outside only. So if leader crashed and it restarted, this file contents are durable. So when it restarts, the first thing it does is it looks into this and sees what are, if any of the requests are pending to be fulfilled. It actually fulfills that and makes sure that the database is up to date. So whenever you process any entries from this log, leader actually removes those entries from the write ahead log.
Okay, okay. So it basically write ahead log provides two things. One is the reduce the latency is one thing. This client don't need to wait until database is updated.
Yes,
Just
yes,
puts
correct.
in write ahead log. Also, you mentioned like even though leader one is down, since it's persistent, once leader one is up, it can pull back data from this write ahead log.
Yes.
So is that lives in the hard disk then?
Yeah, I mean, like in a hard disk, maybe you can just assume this place. I mean, like this place is quickly accessible. Maybe, I mean, like I think we'll need to. I mean, like this is accessible much faster than the real database points, because the real database, if you see, the disks will have multiple layers and multiple blocks. Like, and then there will be something like if you treat like a magnetic disk, it needs to spin to the actual location to actually write. So let's say if there was one location in this disk which was already much faster accessible in the part of the disk, but it's still fasterly accessible. So that's the place I think which normally databases use so to quickly respond.
Okay, thank you, Naga.
I have a question. So when the user run a query, would they also search in the write ahead log at that time, or only search in the database?
No, when the query comes, read query, it only searches in the database. And I'm sure like for the queries, databases will have the query cache, other concepts to serve better. But like this is only for the writes. Write ahead log is only for writes.
Yeah, so let's say whatever the user just write to the database, if they don't search in the write ahead log, they wouldn't see it, right?
No, write ahead is like a temporary buffer, you can assume, because it just keeps the items in write ahead log till before actually writing to the database. Once it writes to the database, it removes the entries from write ahead log. It's like a temporary durable buffer, you can assume like that.
Okay, so when the user, I just want to know when the user issue a query, I mean, update first, and after update, a follow up by query it. And, right now, if the record is in the write ahead log, then you're saying the database would not return that update record.
Yeah, I mean, like, good question, but like generally these entries are like served much faster. Like if something you see that it's still in write ahead log, and if somebody queries the database, the replicas or leader also, it will. I mean, like you won't get the latest data because that is yet to be added to the database segments.
Okay.
So I mean, like you can still observe in SQL databases sometimes, like I don't know which may not be always true, but like sometimes though you insert, you might not get in the immediate next query if you hit. Like it may take like kind of a second or some milliseconds before it writes to that.
So write ahead log to database update is very quicker, right? Then only
it's very quicker. It's actually very quicker. It's just to ensure durability. All databases use this to serve the purpose of ACID. They have to write somewhere, so to make sure that they're durable, but still serving the writes faster. So that's why they use this concept, write ahead log.
Even with write ahead log, let's say we have multiple writer, would that write ahead log get we block it? I mean, we lock it, so one writer can write to write ahead log at a time.
Yeah, it depends. Like if you have multiple writer threads, I mean, like then either you have to obtain the log if you're using one, or use this write ahead log multiple, which is not the case normally. So I think the general idea is like though the multiple threads are using the write ahead log, the concept is that they always append, no update. So this is append only. Even if multiple threads are actually writing, one thread will write to this, and other thread will see that this is empty, so it will write to the next thread. And whichever is empty, it keeps on writing. So if this is growing, means the database writer process is not serving fast. I mean, like not processing the writes faster, because this is kind of, maybe you can just have all the concurrent writes queued up here to be returned to database. It is just a movement where like you will see all the entries here, but as soon as the writes are inserted into the database, then you won't see the entries here.
Okay.
Naga, is it something like a design practice to have logs? Like I've seen this type of log in Kafka also, that they used to have Kafka logs. So it is something like database logs. Is it something like design practice?
Yeah, I mean, like this is one of the, I mean, like I covered one distributed log, what it actually means in one of the topics. So the Kafka is actually built on the same concept. So basically the same thing which I'm talking about here. So the Kafka also works in a similar way, but I think the idea of partitioning and all that like will have to be determined, but they use a similar log concept before actually putting into the partition.
So this is something like a design concept to have a log file on which every writes can happen, and then we can transfer it to the main entries wherever it goes. Okay.
Mm-hmm. Yeah, we should not confuse this log with actually the application logs, which are different, like the web server logs and other.
Yeah.
Yeah, and this distributed log, I mean, like this write ahead log, this similar concept is actually also used in consensus, like where you, the consensus is a concept where you get multiple nodes agree to some certain decision or some value whenever you have some conflicts. So that's another big concept. Maybe we can cover in some other place. And there we can see how this log is actually used, this log concept. It's similar to write ahead log, but it's on the same idea, but like it's little different. and how this is used to solve the consensus, and there are some concepts like total order, broadcast. So there and all, like we use this log extensively. Maybe we can cover that in another session. So I think any questions? I just want to cover now the failure scenario, or like adding a new replica. So if we'll just assume that we don't have any questions, and let's imagine like you have currently replica 1 and replica 2, and based on the load and the read availability, you decide that you need to add a new replica. So how do we add a new replica without disturbing the existing system? So how do we make a new replica replica 3 ready and add to this existing single leader system? So the idea is like you already have some consistent we want to make sure that the replica 3 is up to date, almost like near to the recent on the all the data that all other replicas and leader have before actually adding to the main leader. I mean, like just to make sure that leader is aware of the new replica. So before inserting into this existing system, what we make sure is that like we take the consistent snapshot of leader at some point in time. Like we always have the database snapshots, like taken daily or like maybe weekly ones. We can just whatever was if it was taken on the last week or even last day, yesterday, you can just take that consistent snapshot and make sure that this replica 3 updates all of that consistent snapshot data internally. And after that last week, say after that, maybe like after 325, it says like it asks the leader that give me all the updates after this 325, or it can even ask some of the replicas, whatever they have. So they can ask the leader because it has the latest entries. It can update all of this only after processing after this 325 entries, like to the current latest minute in point in time. It says that now I'm ready to accept the new data. So I'm ready to even serve read request at this point. Any questions on this? I hope no. So this is how we normally add a new replicas.
So Naga, so when we add the new replica, you mentioned that we have to actually take the snapshot and push that snapshot to the new replica. So if we don't do that, so what will be the impact if we directly add the replica?
Yeah, it's yeah. If you don't do that, then it will be a big concern. That's what I see. Otherwise, what you have to do is you have to get the data from the leader. I mean, like even if you haven't done that, the idea what they say that like you don't have any of the snapshots of the leader. So the option at this point available for us is we can temporarily stop leader from serving the request, or even like it can continue to serve the request. There are many databases which will offer you to take a consistent snapshot of the database while it's serving the request. So at this point, I think it actually you can request a consistent snapshot, which may take like, depending on the data size, it may take hours or days before it actually produces the whole copy, like in terabyte file or something. Once you get that snapshot, then you need to take the replica 3 and that file manually and make sure that it updates to that latest that snapshot. And once that is done, it can request the entries after that timestamp. It asks like leader, like give me all the entries after this date and time. So if you don't have, you can still take, and many databases, including SQL databases, support this. And if they are not of support, in the worst case, you might need to temporarily stop serving the request, so the databases can do the snapshot quickly, and you can just take that and you can enable the leader to start serving the requests again. In the worst case, we'll have downtime, but normally all databases offer you to take a snapshot of the databases without turning off or serving the request.
Okay. What I wanted to know here that, I mean, if we don't have the snapshot and we introduce the new replica, so still that replica will pull the information from other replica or leader, and that will be from the start. So it will slow down the process to actually get up to date that replica. So is that possible, or that's not possible at all?
You mean like, are you saying like there's no way to click a consistent snapshot, and then in that case, what is the case?
I'm not saying that there is no way. I'm just saying that whether if I just introduce a replica without having a consistent the snapshot, so it's still possible that that replica will be able to pull the information from leader or other replica.
Yeah, it still needs to pull, because without that it cannot serve the request, right? Read request in this case. So without having that latest data, the assurance, we cannot add to the existing system and say that serve the request. If it has some old data, or like it doesn't have any data, there is no point in adding to the system. And I mean, like since it won't be able to serve any request and take some load from the existing replicas.
Yeah, that makes sense. Yeah, just I want to know that whether it's possible without that or not. But you said that yes, then I'm okay. Yeah,
it normally, we just need to make sure that it has at least recent data. So this is one of the methods to get these replicas up to date. And as soon as it is up to date with those, then it can start serving the request. So, and now,
instead of taking the leader down, we can take one of the replica down, right? And then take a snapshot of that replica and copy to the new one. And that way the system is still running.
Yeah, that's also a good idea. Yeah, I mean, like as I said, like it's only the first time. It need not go to the leader. It can take any replica and just get as much information as it needs. So you need not take the snapshot of the leader also. You can take from replicas also. But only thing is that before it announces that I'm ready to serve request, it needs to go to the leader just to make sure that it has latest copy. Because all the replicas, the general idea of replicas is they always go to the leader get the latest updates, right? So this also needs to go to the leader just to make sure that give me the entries after this. If suppose if this replica 2 hasn't received few writes or hasn't processed few writes, and this replica 3 might get those from the leader, and before announcing it's ready to serve the read request. So yeah, on the consistent snapshot or like the backup snapshot, we can take from many replicas also. Yes, thanks for mentioning that. And there is another concept now, like I just mentioned that these replicas all go to the leader to pull the latest log or this write ahead log and process the entries, writes. So there's another way is like the leader can always make sure that it just updates replica 1, and this replica 1 needs to make sure that it updates replica 2, and this replica 2 needs to make sure that it updates replica 3. So this kind of responsibility is called chain replication. So some places, I mean, like I think even in Microsoft also uses in some of the Azure databases, I think, or like in Azure platform, this chain replication concept. So then the idea is like instead of leader updating all the replicas, it can just update whichever nearby replica, and those replicas will in turn have the effect or like the responsibility to update other replicas. So that concept is called as chain replication. In this case, only issue that we see is like if in case the client wants to read and it connects to that last replica in the chain, so then the latency or the stale data chances are higher if it goes down the path to query. But like on the performance wise, this is better than the single leader pushing the write-ahead logs to all. And I will move on to the next one. So I mean, like next concept, like what happens if leader failed. So anyone has any questions? So let's say like now we have this one leader and two replicas. And what happens if leader gets failed? So we need to make sure that if leader is failed, we need to make sure that one of this leader, replica 1 or 2 takes over the leader and announces itself as a leader. So how do we pick the replica 1 or replica 2, or if we have another replicas, like what are some of the mechanisms that we normally consider when choosing a new leader? So one of the strategies could be that like whichever replica has the latest entries, I mean like in terms of the writes, whichever like in this log, in this write ahead log, or in terms of the writes, we just see which replica has latest data. So this could be one of the strategies to pick a new leader and announces itself as a leader. But whatever the decision that that any of the replicas take, they need to mutually agree. If there are like another replica 3 also, all of these replicas need to mutually agree and come to a consensus that yes, replica 1 has the latest data, and let's make replica 1 as a new leader. So this decision is taken through consensus. So as I said, like this concept makes sure that all nodes agree to some value, and this is a trickier concept. I mean, like we can, as I said, like we can talk about this, how this consensus decisions are made. It's not just in this leader elections, there are even in kind of conflicts. This kind of scenarios occur where like you get multiple conflicts, and then we need to decide which will be the value that we agree on to take. So there are many decisions on which like many nodes in the distributed systems need consensus for. So this is again kind of a new topic which we can go in depth, and it takes time to understand. So you just assume that the nodes agree on some consensus and one of them becomes a new leader and they take over. And anything that I forgot. So any questions so far?
So how does the replica know the leader is no longer available?
Yeah, good point. So one of the strategies could be that like this replicas can keep pinging the leader, like they'll have the heartbeats or something, right? They keep receiving. Suppose it hasn't received writes for some time, or like they'll have the periodic heartbeats, which we call. so to the leader, and if leader doesn't respond for certain time, or there are certain number of writes continuously failing on timeout, so there need to be a system which monitors that these writes are continuously failing or failing with timeout or continuously erroring out. There are some conditions on which you mention that this leader is failed and is no longer serving. Then this replicas will need to arrive at a decision. So normally this could be done at a load balancer level where all of the nodes and replicas or leaders heartbeats are at load balancer, or there could be a system like Zookeeper which monitors all these replicas and like a configuring system which keeps monitoring all these replicas as well as nodes. And if it figures out that this leader heartbeat is not responding or timing out, then it takes or it sends instructions to all the replicas, or it may itself choose a new one of the replicas to become a leader based on whatever the consensus algorithm that we choose. So let's and then it announces that this replica 1 is the new leader, and client when writing requests they may be using one of this load balancer or Zookeeper to make sure that it knows where to process the writes.
Okay, so I have a question. Let's say the replica cannot communicate with the leader, not because the leader was crashing, but because of the network, partition or the network problem, right? And then now, on the other side, the replica 1 get promoted to be a leader, right? And at that means at that time we have 2 leaders, right? And then after that, the network partition was fixed. Now, we have 2 leaders at the same time. Then who would be the main one?
Yeah, good point, and it's a good question. So this leader, like suppose if for some reason these replicas were not able to, there is a network connection, and these replicas were not able to reach to the leader, and this Zookeeper aware of that, and it makes a replica 1 as a new leader. It makes this as a new leader, and all the client is made aware that or some clients may be writing to the old leader, and for the new clients, when they get the configuration from Zookeeper, it gets sent to this new replica 1, which is a new leader. And then once this connection is re-established, or once the Zookeeper or replicas figure that this old leader is still available and ready to process the request, so this is the old leader, and according to Zookeeper and all the other replicas, they all agree that this replica 1 is a new leader and it's serving the request, and they figure that this leader was serving some request, and they send communication to this leader that you have to become a replica now, because we all agreed on a new leader. For some time, some rights may be lost, whichever return to the old leader. In that case, when this happens, it's also called as a split brain. Not split brain. I think the split brain is there are 2 replicas which they decide that it depends on this algorithm. So if we don't have a proper algorithm, there is a chance that replica 1 says that I will become a leader, and replica 2 says that I will become a leader. So we have to make sure that choose a correct algorithm always to ensure that only one leader gets elected, not multiple ones. So in this scenario that you mentioned, there will be some rights which return to old leader might get discarded, or we can have a mechanism to make sure that those rights are processed by replica 1 the new leader again, and we need to definitely make the old leader as a replica, because we already chose a new leader because it was temporarily unavailable.
Okay, but we also need to sync the data too, right? Because old leader have new data, but new leader also have new data.
Yeah,
How would you sync them?
Yeah, so that's another concept, but I think if we step into that, so it's about like since the rights, we will need to deal with the right conflicts. So that's one of the scenario of right conflicts, because the old leader also has accepted and new leader also has accepted some rights. So the good practice is to merge, and there is some concept of version vectors, but we will deal that to solve the merge conflicts. But we can use, we can talk about that in some other session. Like there are many other issues in single leader application, like the problems that you see with replication lag. The lag is actually the delay on which the write came to leader, and it's said to be arrived in replica 3. And what are the problems that we see and the write conflicts? All maybe we can cover in some other session, if that's okay. We will talk about the high level how the replication works in all the three today.
Yeah.
Any other question? Okay, I'll move on to the multi-leader now. So, I mean, like I forgot to mention some of the databases, like most SQL databases support this single leader, including like MySQL. I think Oracle mostly uses that, but there's some version of Oracle which uses single leader also. And then among the NoSQL, there is a DynamoDB, not Dynamo style. This is DynamoDB and MongoDB. I think there are a few other databases, and here also Postgres. And even Kafka has this, it supports two modes, Kafka, leaderless as well as single leader. So, and then RabbitMQ also uses this. Yeah. So, yeah, many databases still use a single leader, and we will talk about multi-leader now. So the multi-leader, the advantages of multi-leader over this, we will just check in a moment. Just a minute. So let's say that we have leader 1 and it has replica 1, replica 2, and this leader 2 also has a replica 1 and replica 2. And there is some naming terminology. I always use single leader replication, and it's also called as active passive, or it's also called as master slave. And this is also called as master or active. So I mean, like, but for now I'm just using these terms, but like it's also called as this. So don't get confused if somebody mentions active or master or active passive or all these terms. So how does a multi-leader replication work? Let's take a look at that. So The problem with single leader, like we always have only one leader serving all the rates. So let's imagine like your users are spread across all the globe, or like across the regions, and your leader is actually say in US West or like US East or in Asia somewhere. And if there are some consumers or clients submitting the request, it needs to go to that specific leader where it was, and then like the latency is higher in a single leader application. So for those situations, like this multi-leader is often a good choice, where you can have a leader in each region. Like this is in region 1, and this could be in region 2. So any request, any clients connecting from this region, you process, the rights are processed by this leader. And if some client is connecting here, then this leader will actually process the rights. And I mean, like this replicas are inconsistent with this leader, and this replicas will take the data from this leader and be consistent. So the read request for this region, for the read request for this. So any questions? Like the advantage with this is, even if the whole data centers is, let's say, wherever this leader and replicas in this region 2 is, the whole data center went outage, you still have this leader 1 or like the region 1 data center up and running. So you can redirect the rights from even other regions to this region to continue serving the request. So with this multi-leader replication or master, you can bear a whole data center going out, or like the whole data center outages. And the other advantage that we saw is like its network latency wise is better. Like as long as you have the leaders closer to the user, rights are served much faster with low latency. Any questions?
So how did the data gets synced between leaders?
Yeah, good point. So I was about to come to that. So again, like as we talk, I mean, like as we spoke in a single leader, the same mechanisms can be used here. So we can make sure that like one of the choice is synchronous. So with this, the advantage and disadvantage is that whenever the rights happen to this leader 1, it cannot acknowledge the client. If we choose synchronous, it just needs to get an acknowledgement from leader 2 that it has accepted this right, and then only it will respond to the client. In this case, the advantage is that you always have the latest data across all the regions. But the disadvantage is that the right will take some, I mean, latency hit. So rights will take actually some time. In this case, though it's only writing to the leaders, but if you have 3 or 4 leaders, then the amount of I mean, like the waiting time to get the acknowledgements from all the leaders that the right is successful will take some time. Like if you have 3 leaders, 3 leaders processing the request, and each of them takes some 200 milliseconds, the total write time will get increased, right? Like it will become 600 in this case again. So to process the request. Whereas if we choose async, so this is one of the strategy, and we can also choose async. In that case, like whenever client writes, as long as this leader accepted, it can just immediately respond the rights, and this leader will need to asynchronously update all other leaders. Like I just took one example now, leader 2. We can have leader 3 and leader 4 in some other regions. So this leader 1 will need to asynchronously send an update to all the other leaders, and all the other leaders, as soon as they process this async update, then they'll be ready to serve those queries solved. But as we can notice, like in the async, it is possible that as soon as if somebody writes a data here, if somebody else is reading the data from other region, the same data, you will get the stale data. I mean, like not up to date data. So that's one of the disadvantages. And there is one other issue, but before getting to that, any questions? Okay, let me talk about, so what other issue could come up in this multi-leader application. So one of the scenarios is that chances are low, but let's say if this client one here and another client two here is updating the same record at the same time. So he sends an update to leader one, and this client one also sends an update to the leader two for the same record. They both, let's say that they are choosing async. They don't wait for other leader to acknowledge. So they just say that your write is successful. This leader also says that your write is successful. But when they send each other the updates, they realize that this update is actually meant for the same record. So the situation here is like both have successfully acknowledged the writes, that your write is successful. So here also we have we need to deal with this write conflicts. So if we choose this async, but the chances are not very high because but still you need to deal with write conflicts. So yeah, there are many write conflict handling data structures. And again, this is another concept. Probably we can take this write conflicts along with when we look up the issues on single leader and multi-leader, what are the issues that could come up? Write conflicts is one of them. So there are few possibilities. One is that you merge, or the other possibility is that you make sure that the last write always wins. So among these two, though in this case they both are writing concurrently, we should not take consideration into time, but still if you take that strategy of saying last write wins, so you end up losing some data. So some of the mechanisms are to merge both of them and in a sensible way. And for that kind of a merging, how to merge those kind of data, there are some data types and some mechanisms to handle all these conflicts. So we'll probably look at those in some other session. Any questions?
Somehow we have to notify the user too, right? Before we acknowledge them and say, okay, that's success. Now it's something else.
Yeah, I mean, we need to definitely acknowledge the user. So one of the I said possibility, if it's possible to merge, the people will actually merge. And so I mean, as I said, I wanted to cover this in others, but further strategy, as you said, is whenever we notice this conflict, if you don't have a choice, but we wanted to be kind to the users, that we can echo back to the user saying that we received the same, and which one do you want to prefer? That could be one of the choice of solving this. But from what I noticed, the system will try to resolve itself if there is a possibility. So that's all. In that case, that's always recommended. But there are scenarios also come up in leaderless. So there are some situations where they merge, and some situations where they send this conflicted data. They still store both versions in the same record, as an appended or something. And when client reads that, they figure out that no, it should be this instead of this. This is the latest, so they can resolve the conflict and then update back. So that's also another mechanism. So yeah, we can talk about this in detail in another session.
Okay, Naga.
Any other questions before we move on to leaderless? Again, like each of this is kind of a trade-off whether you choose single leader or multi-leader, and I will also talk about what leaderless means.
Sure.
Okay, let's move on to the leaderless now. So we looked at single leader, and we always have a single leader, and here we'll have multiple leaders serving the write request. The concept of leaderless, as the name suggests, that there is no leader at any point in time. So in that case, like how does it work? So let me take some example. Let's say that these are all the nodes, some A, B, C, D. So we have now four nodes, right? Like the concept of leaderless is like anybody can serve the reads and writes. So that's the idea here. So if some client is connecting to B, so it will become the coordinator node to serve the reads and writes. And sometimes in this scenario, I'll talk about what the coordinator's responsibility. Sometimes there is no coordinator, but sometimes there is a coordinator. It depends on some databases. Some they choose to provide, some they don't. And if some clients can also send to any system which they can reach to, can accept the reads and write and serve. But to be able to successfully write, or there is some concept called quorums. So the idea of quorums is, let's say you have 5 nodes. Out of this, you say that at least 3 of the nodes should accept writes successfully. So you say 3 of them should process the writes always successfully. And whenever you want to read the data, you say that 3 nodes you have to read always. So this is one of the example quorum. So this quorum relies on a condition that any data you write to a set of nodes, you can have as many as you want. Like you can have 10 nodes, but you say that any data which is being written will always be returned to 5 of them, and that data for that client always go to the same 5 nodes. But to acknowledgement a write, you just need responses from 3 of those systems. And to acknowledge the read, you just need to read that at least there are like 3 systems for which you need to write. So let me type this to fit another. Let's say you have C here, also E here. Let's take this scenario of 5 nodes quorum, and when this client is writing some data, some node, some data, maybe it's some object, an object or something, some of P1. So this P1, when it sends to this coordinator node, and if this figures out that these are some of the 5 nodes, these are all the 5 nodes for which the data P1 is supposed to be stored, it sends request to all these 5 nodes. It sends request to all these 5 nodes, and when it receives the responses from at least 3 of them, it says that your write is successful to the client. Send success response. It doesn't actually wait for all the 5. Similarly, if client wants to read this P1 data, He connects to this coordinator node, and it again sends request to all the 5, which is supposed to go, but it just expects the responses from 3 nodes. So this, as long as you read the data from 3 nodes, you check which is latest among the 3 nodes. Because if you are inserting data to all the systems, let's say A succeeded, B succeeded, C failed, D succeeded, and E failed. Right. So since you got a response from at least 3, this is 1, this is 1, and this is 1. So this 3 succeeded, and this 2 failed. So as long as 3 succeeded, you send success acknowledgement. Now when you get a read request, you read from all of this. Suppose that these 3, this. So the B and C, which is failed 1, and E failed 1. These 3 came with response quickly. So since the 3 nodes responded, the read is successful. So among the read, it figures out that which node has the latest data. So in this case, B processed successfully. B has the latest data, but C and E, which failed to process that request, were having the old data. So in this case, what B learns is B has the latest data, and C and E haven't processed successfully. So let me update them with the correct data. So this coordinator node, in this case for this client, knows that C and E are out of date, and it updates the record. And first, it's actually sends a new data to the client, whatever he queried. Then it actually updates this asynchronously. So, any questions on this quorum concept? I don't know if I made sense.
How does it know it? How does it determine which one is the latest data? Because there's no global clock.
Yeah, good point. And one of the strategies for determining the latest is like if you rely on the time, which is always bad, because the clocks could be not synchronized across all the nodes. That is one of the issues. So what actually happens is like all of this actually maintain the versions. As I was talking about, there is something they all maintain to know that the version vector, whenever it updates some data or it returns some data, along with the data, there will be something called this is V1 or V2 or something, which represents latest. If you have the higher the version, it indicates that it is higher the latest the data is.
Okay.
So any other question? Like, have you all at least understood what a quorum is? Like how the leaderless normally works?
Can you please explain it a bit again?
Okay. So the idea of leaderless, as I said, is like you don't have a leader, right? So whenever client wants to write some data, suppose like in this case, clients 2 wants to write data, and we have this 5 nodes, A, B, C, D. So our quorum condition, so this is the condition on which all the leaderless systems work on. This condition says that out of 5 nodes, if any of the 3 nodes acknowledge a write, treat this as successful. And whenever you read the data, you at least expect a successful read response from 3 of them. So then you can serve that read. So that's a quorum condition. Now that client 2 has sent the data P1 about the person 1. So it and he is currently acting as a coordinator. So which means that it is accepting the write on behalf of the client, and it knows which of these 5 nodes are, and it sends the write request to all the 5, including in this case itself. So at least 3 of them respond successfully. In this case, we told like A responded successfully, B responded successfully, and D responded successfully. So C and E failed to fulfill the request, but still our condition is met. So the D knows that 3 of the nodes were successfully processed the write, so it responds success response to the client. As soon as it responds, it receives a response from 3 nodes, in this case A, B, and D itself. So now this client 2 came with another query for the P1 data, and D knows that these are the 5 nodes which are serving that client. So it again sends a request to all the 5, including the failed nodes. I mean, like including the nodes which failed to process that write. So, and then this time, instead of A, B, D responding in the right case, this time B and C and E. So B was the only one success node which processed the write, but C and E didn't process the write, so they have the old data. So let's say that B responded with, I don't know if this is visible. Let me write it here. Let's say if the latest version was V2, B responds with V2, and C responds with V1, and E responds with V1. So now the D coordinator nodes looks at this person data, and it's B is returning version V2, and C is returning V1, and E is returning V1. So the quorum condition is met because 3 nodes return this data successfully, and D learned that C and E have the old data because B has a V2. So it knows that it needs to send V2 to the client as a read response. So in the read response, it sends the V2 version data of the person P1. And since it learned that C and E failed, I mean, like doesn't have the latest data, D after sending the read D after sending the read response as a coordinator, it ensures that C and E are up to date. So it sends the writes again to D and E internally, just making sure to sync them with the latest data. So is that clear?
Yeah.
Okay. So as you notice, like in the quorum condition, you are making sure that out of 5 nodes, at least half, like half of n or whatever the nodes that you have plus 1. So this plus 1 is what which makes sure that whenever you read, at least you are making sure that one of them will have the latest data. So defining this quorum conditions, I defined that P3. If I would have said 2, 2, there would have been chances that I would have read from C and E. I would have read stale data.
So doesn't any sync up happen after that? I mean, if any write happen to D, and it gets acknowledgement, success acknowledgement from the 3 of nodes, which is success according to the quorum condition. So, but the 2 nodes which is left, does any synchronization happen afterwards? I mean, after that request?
Yeah, I mean, yeah. The scenario here is that though you are saying that as long as 3 nodes which process them write quickly, there are chances that the other 2 also finish the write, but they process late. So the coordinator node doesn't send the request to only 3; it sends to all the 5. But it expects response from 3 of them only. So there is a high chance that even the other nodes process the request. But make sure that it's highly available, and in the quorums, the advantage is that it can serve the request faster and with low latency. Because whichever the nodes process this 3 might be quicker, and they'll be processing. I mean, like this write as compared to other methods, like here it is quicker, and also you make sure that at least 3 of the nodes have the data. It's happening in parallel, right? You are not waiting one after the other.
Okay.
like in later applications. So that's one thing. And there is one thing I wanted to mention. I forgot that. Okay, I think as soon as I remember, I'll tell you. So whenever you decide a quorum, you always need to make sure that there is at least one overlap. But in reality, the number of nodes could be much higher than the given quorum condition. So in this example, I mean, like we can say that the number of nodes available to process the whole system may be 10, but you are defining a quorum of 5. So you can satisfy this quorum condition, like whenever the client writes something or reads something, you can always make sure that this client always goes to these 5 nodes. That configuration could be kept somewhere. Like it could be known to the client upfront. If we don't have a coordinator, we can let the client system in our system only, like which is consuming or processing these writes, it can be made aware of which all the nodes it needs to go to. But if there is a coordinator, this itself can figure out using the data from client 1 or like the client 1 IDs. It can always determine that whenever he sends a data, these are the 5 nodes we need to go to. So like the consistent hashing can also help in those cases. And in this kind of systems, it's always common practice also to use Zookeeper to maintain. We can also always use a Zookeeper to maintain the host information, like all the health information, so it can keep track of also the quorum conditions, everything, all the metadata about all these hosts and nodes. You can use the Zookeeper to track the health and update and also the quorum conditions to help in this case. And that's how most of the systems even work. So the databases which use this kind of concept, the famous ones are Cassandra and Riak. Facebook, Cassandra, and Riak. And I think there are many others latest in the market, but like these are the 2 ones which I know. So this is the similar concept is followed there.
What is the maximum number replica you have seen? Like, you know, like 10, 20, 30 or so?
So here, like instead of, I mean, like replicas, like as part of quorum, you make sure that at least 3 of the replicas or 3 nodes which are carrying the same data. So this is kind of the number of replicas you want some data to be stored. That's as part of defined as part of quorum.
But let's say, because I'm thinking, let's say we have like 100 node, right? That means if we write to one node, we have to make sure that like 51 of them response. Then if, you know, that to get all 51 of them response, that's gonna time consuming, right?
Yeah, I mean, like, so that's why I wanted to give this example. So yours, I said here total nodes are 10, but the quorum condition is only 5. So you have 10 nodes available. So if I have like from clients from other region or some other place, I can still use the, I mean, like some nodes which are part of this quorum could also be part of other quorum. Suppose, let me write to make it better. So this is one of the quorum, right? Let me write some other quorum. So now I'll have this F and G, whatever now, and at least one other node. So H. So I can form a quorum with B and C and G and H. So this has one another. So this is kind of another quorum 2. This is quorum 1. So this quorum 1 will be the quorum for if some writes are coming from these clients or some certain number of clients. and this set of servers could handle some another set of clients or some other part of data. Suppose in the sharding or partitioning concept, let's assume that sorry, don't know where to write. So let's assume that this serves all the person names who starts with A to M, and this could serve all the nodes which could start from N to Z. So this could serve certain part of data load, and this could serve certain part of data load. And this can be completely disconnected also. So if my total nodes are like 20, so 5 nodes actually serve A to M, and another 5 nodes could serve N to Z, or like since I have many other nodes, I can all form like disconnected sets of partitions of columns which are serving certain sets of loads. But in this case, I just made it overlapping, but even this is possible, just to show. But they can be disconnected also, just like we have seen the partitions, how the partitions work. Is that clear?
Yes.
Total number of, like in your case, like it could be 100, but the total number of nodes which are storing that data could only be 10 or 5. You can always make sure that same client or the same data gets to the same set of nodes using the consistent hashing or some other mechanism which routes only to those nodes whenever the similar request is received.
In that way, the network traffic in each quorum will be smaller.
Yes, correct.
Yeah.
Correct.
Okay.
So, yeah, so you don't need to always assume that you half of the nodes you need to make sure that right, and this would be an example for smaller systems. But when you go like bigger, like you cannot rely on that condition. You'll have to shard the data and make sure that's split accordingly. So now, if no other questions, then I'm going to get to those actual topics. I don't know how much time we have. We only have 30 minutes. I hope I can cover those concepts.
I have a question.
Uh-huh.
So if suppose there is a write to D, and first it will do the write operation, and then it will try to fetch at least 3 of the successful writes, right?
No, not like fetch. So what happens here is like, let's say, as a client, it submits the write, right? So some record one, like person one data. So this is the write request. So this coordinator node needs to accepting this write, and it needs to acknowledge the write. Before acknowledging the write, what is the condition? Our quorum condition is like of the node should respond. In this case, if since the actual quorum is like 5 total nodes, the coordinator responsibility is it should send the request to all the 5 nodes. This write which came from the client, this distributes to all the requests, I mean like all the nodes in this quorum, which is this all this ABCDE, this case including itself. So what it needs to do is like it needs to wait from at least 3. If D has fulfilled the successfully and A has fulfilled and B has fulfilled, it knows that like it received the acknowledgement from A, it received the acknowledgement from B, it hasn't yet received C and E. But since it already processed and it also received from other 2, the total condition is reached for write. So 3 conditions successfully processed. It doesn't wait for C and 3, so C and E. They will be still writing and they might even acknowledge later, but it doesn't care. So as long as 3 responses are successfully acknowledged, it acknowledges the write. It sends acknowledgement that your write is successful. So this C and E could still send the acknowledgements later, but this will ignore, saying that I already responded. So they could even fail. So in that case, it doesn't care. So it already acknowledged the client.
Yeah. So my question is, what if it didn't get at least 3 acknowledgements?
It doesn't acknowledge, it doesn't send the response to the client. It's still waiting to be fulfilled. The right is waiting to be fulfilled. So it is possible that if all the quorum nodes are gone, like they are not available to fulfill the rights.
Yeah, kind of. Maybe it gets only two.
Then it's kind of a right fail. So this is the, I mean, like as long as this is a quorum condition that I'm always living to. So let's say this is a strict quorum. We always ensure that this condition is always met. In that case, this will fail. This right will fail.
Then will it undo the right operation on D also?
I mean, like in this case, there is no undos and all. Like it's just that right got failed. There are some mechanisms we can get over this with.
But few of the nodes which have successful data, so it has a wrong data, right? Like our right operation has been failed, but few of the nodes which have successful rights have the wrong data.
Yeah, I mean, like if D was the only one node, so it actually, I don't know if there is a failure response like 200, or sorry, 400 like in HTTP. It can send the 500 outage error, and it can even ignore that. So that's a possibility. Yes, it can discard that right, including in itself, because it was not successfully. It was not able to reach all other nodes. So only this node is available. So it cannot accomplish the quorum right. So it can discard the right and say that failure right response, like maybe 400 or like in HTTP sense, or 500, depending on what your conditions.
It can also happen in D and A also. Like it happens successful, able to write only.
Yeah. So as long as like the coordinator nodes can be any of these nodes. So in this case, client connected to D, but there is also possible that client can connect to any of the other nodes. Any of these nodes can become the coordinator. So it is possible that this quorum is not reached when all of these nodes are like go for offline, some bad network thing happened. So in those cases, it is possible that these nodes can fail to process, I mean like fail to reach the strict quorum condition, and the right is failed. So you are not able to fulfill.
Okay. Yeah.
So this quorum, you can, as I said, as we are talking like 3 needs to acknowledge the right, and 3 needs to acknowledge the read. So you can, in this quorum condition, you can accommodate 2 failure nodes. So if the failure nodes increases beyond 2, this won't be able to successfully process. Like this is the bearability. So according to your quorum condition, you can say that I can only bear 2 failures. So depending on your availability guarantees, you need to make sure that these quorums and these factors will need to be adjusted accordingly. So if no questions, I'll get along the same concept continuation of this issue that he brought up. We can use this sloppy quorum concept. So let's say, like according to his question, sorry, like we forgot his name. So if imagine like three of the nodes are failed, like only D is up and running, you cannot reach a quorum. So, but what if you know that at least like F, G, H, all these are up and running, but like only this set of nodes in this area, like all these nodes got failed. How do you ensure the promise of availability? Can you use these nodes, available nodes, because like we have according to the quorum, we still have 3 nodes, but they are not part of this quorum according to this client. So can we make sure that this data, that person one data, can we store in any other of the 3 nodes apart from the normal quorum? Like because these nodes are temporarily like they're all like down. So we can, with the sloppy quorums, the concept is that if you figure out that this set of nodes are down, you can temporarily ask, say this FDH, or like within this quorum condition, you can say that since this, if this coordinator knows that these FGH are available, and they can send the write to all of these guys. And if this guy's response saying that successful, you still meet the condition of storing this data at least in 3 nodes, but these 3 nodes are not actually meant to store this data of the client one. But the idea is that they are not storing permanently. So once these nodes figure out that this A, B, C nodes are up and back again, it can send the data back to A, B, C. So it is just temporarily acting to serve the write request without losing the, like kind of write availability. You are increasing the write availability by making use of other quorum nodes to temporarily store something. And as soon as these nodes are up, they will send the data to ABC. So this concept is called as sloppy quorums and hinted handoff. So since it's not ensuring the strict quorum of only this node storing the data, that's why it's called as sloppy quorum. So we at least, as long as some n nodes, or like in this case 5 nodes are available, like this 5 nodes are available, or like when the D and E, if these 3 are failed, D and E and these 3 are able to accept the write request, and 3 of them, these 3 were able to successfully process. In that case, this quorum is not strict, that's why it's called as sloppy quorum. But once these nodes are up and back again, they will hand off the data to those primary nodes. So that is called handoff. That's why like that algorithm or technique is known as sloppy quorums and hinted handoff. So this is mainly in leaderless applications only. So with this sloppy quorums, the advantage is that you are still serving the writes despite so many number of failure nodes. But the issue is that once these nodes are up, till the handoff is done, they may be like temporarily unable to provide the latest data. But still you are accepting the data and storing the data from the client somewhere in your systems. So your availability is increased in this case. So you can tolerate maximum number of failures in this kind of sloppy quorum techniques compared to the original strict quorum techniques. So it's by default in React, but I don't know about Cassandra. Tell me.
But still, read will be for read we still get the old data, right?
Yes. So
or may not be available because the quorum will
not be available because these nodes are temporarily gone. Some network connection disrupted these nodes, and they're not able to. D is not able to connect to A, B, C, but D is able to reach to E, and D is able to reach to F, G, H in the cluster somewhere. So since it's not part of the strict quorum, you are temporarily storing the data somewhere, and the reads also you can. I don't know, like since the 3 is a condition, it cannot fulfill in this case. The reads also, I don't know if you want to do follow the similar approach, like by reducing the read availability. In that case, like you just read from these 3 nodes, like 2 nodes instead of 3. So it's not a strict quorum, but you are still serving the read request with some stale data.
Okay. So
these are some of the compromises which you can normally discuss if this kind of issues come up. These are some of the trade-offs which we can discuss. Like if you want the system to be highly available, in those cases you can make these compromises, but you are sacrificing the consistency in this case.
Okay. So sloppy quorum strategy is only for write.
Yeah, mainly, it's able to write, and even for writes, I think you can, as long as you minimize this R in the worst cases, you can still serve. This quorum is your condition, right? What if say, I just wanted to make sure that I just read in 2 nodes and write in 2 nodes. In these cases, this condition is still, you can do that, but compromise you are doing is there is a high chance that you always read the stale data, because you are only writing expecting success response from 2, and for reading, if you're reading in 2 nodes, you could end up in other 2 nodes where the write was unsuccessful, and there's a chance of reading stale data. But you can, whenever you figure out that, you can update those data. And there is some other process which I will talk about now. It's called anti-entropy, and we can show that how we can make sure that other nodes up to date with the data.
What is the best practice to actually select that the quorum count? What is the best practice? What that number should be?
Yeah, I mean, like, this is normally, I mean, like, at least half of the nodes plus 1, that is good practice, because that at least ensures that like, if you have the 5, half of that plus 1, so you can tolerate, like, if your nodes count is like 2f plus 1, you can always tolerate this f failures. So depending on this availability, so this formula is generally good. But for few cases, if you can use the techniques like sloppy quorums, and there is also to make sure that the other nodes are not falling too much behind, we have some background task. That is the next one, anti-entropy. So that's what I'm going to talk about now. So we will see how this anti-entropy helps in this quorums.
Okay.
Any questions before I talk about that? Okay, so that's about sloppy quorums and hinted handoff. And anti-entropy, this is actually the process. Like, so one of the technique that we talked about, like, suppose in this case, the first scenario I said, like, the write was fulfilled by A. Let me write this again. So among A, B, C, D, E, I think this is visible. Okay, let me write E. So if this failed and this got success, this got success, this got success, this failed. So this, among these 5 nodes, 2 of them got failed. Now D learned that in the next read request, and it does a repair on E and, sorry, yeah, in this case D failed and E also failed. It does, whenever it gets a read request, it reads from other ABC nodes, or like one of the 3 nodes will have the latest data, and it learns that D and E are out of date. So one of the mechanisms to repair the updated data, like the outdated replicas, is through read repair, so which I talked about previously also. So with read repair, we can still make sure that some nodes are up to date, but it's possible that some nodes might never be reached and they may be completely go out of date. For that, we have a background process known as anti-entropy. So this anti-entropy is like a background process which keeps checking all the nodes. What is their level of data? I mean, like, whether it has latest data or not. So this anti-entropy, let's see how that works. Where is this? So there will be a background process, like if this node has some level of data and this node has some data, so we can use some mechanisms like some data structure for this purpose, which can check the data of A and B and C and D and quickly, because these are large databases. They will be like of in gigabytes or terabytes, right? So you can, if you want to manually or like compare the data in a brute force way, like check all the 1 terabyte of data or like 1 gigabyte of data line by line or record by record, comparing with this you know, like how much pain or time consuming the process is. So there is a data structure which can help increase like a quicker way to compare. So the data structure is called as Merkle trees. So the idea of this Merkle trees, they're nothing but a binary trees. So each node will have two tail nodes, and this child nodes will have again every node will have two child nodes, like in this case, and each node will have a hash value of its children. So if this is A, this is B and C, this is like D. I hope this is visible. Okay, this is F and this is G. So let's treat these are all as leaves. So this D, E, F, G, let them be like the leaves in a binary tree. And so the root will have the root hash of B and C, and this C will have the hash of C, D and E. So it's kind of hash of D and E. So this will become like a hash of F and G. This leaves nodes, they actually contain the records. So let's say this is record of person 1, this is record of person 2, this points to record of P3, and this points to record of P4. So this leaves will actually have the hash value of those tail records, like the person 1. So this will have hash of P2. So this will have hash of P1. So this will have hash of P3. So this will have hash of P4. So the B's hash will be constructed using this child hashes. So this C's hash will be constructed using F and G's hash. So the A will be constructed only using B and C's. So this goes further up the chain. If you have to, so in this case, there will be a Merkle tree which is built for each node here in your quorum. So if the root hashes of D, the node A and B differ, which means that one of the node is out of date. So you check again, you go down the path. So in the A and B, like if you are comparing, I mean, like if I take another tree on the right hand side, there will be mismatch either on the left branch or right branch. It could be both, but like there's a chance that only D got changed and this changed B's hash and A's hash also got changed. Though one node got changed, the whole hash got changed in the tree. The root hash will be changed. In the A, like similarly in the other node, you also compare like which node it got changed. You go down in both the trees level by level and make sure that which node is out of sync, like which nodes are not matching, and this D and E will be compared, which has the latest version of data, and the other tree will get updated. So the way, I mean, like if you see, though one record got changed, you are just updating this before data. In this case, if this was changed, you are not updating all other trees. So to reach to this, it will be like, you know, right, the binary trees you can reach in log n. So
Can you repeat the process of comparing?
Okay, let me erase this to make it better.
Is the concept is something similar to binary index tree?
So let me see. So you just imagine like you have another tree here. So this tree belongs to node A, and this tree belongs to node B. So the root, if you are comparing, it got deferred. so it's not matching. Then you check each child here, the similar B here or C and D, E, F, G. I mean, like it could be any index numbers or whatever it is. So you check this B with this B. So this got, this is not matching, but these are matching. So this is matching. Only this record got changed in this also. Now you compare this P4 here and P4 here. Say this has version V2 and this has version V1. You just knows that this has the latest data, and you update this node B, child D, because this is the latest. You just update this to V2 and update its hash. So this will match now D, and it is corrected. Now the B's node will need to be recalculated using D and E. So this will also get corrected. And since this got changed, this also gets corrected. Now this both roots match.
Okay, yeah, clear.
Okay.
So this version 2, how does it know that the version 2 is the latest? I mean, is there a timestamp, or like how does it know which is the latest data?
Yeah, I mean, like, so first it compares the hashes. Only the leaf nodes have the data in the Merkle trees. So when you get to the leaf node, you just see that like one of the, as I told, like in this quorums, there will be a version data along with the record. In this case, the node EAS, leaf node of P4, version 4 record as version 2. But in this node B's leaf node of D, it has version 4 with version 1. So this version 2 is later than version 1. So you can use a logical number to indicate versions like 1, 2, 3, 4 instead of timestamp.
Okay.
So whenever you have the greater version, it means that this has the latest data.
So that update would be lazy, or is it something like at the same time?
So this Merkle tree is like they will be constructed for each writes happening in the replica. There will be some background process which happens like some runs periodically and checks which are the replicas, whether the replicas are, they will compare the Merkle tree's roots, and if they figure out something is out of date, then it updates. This is a background process which keeps checking the Merkle trees and syncs each of the nodes. Is that clear?
What happened if like you know, the later one is the one we don't want to keep. We want to keep the earlier one. So in case, like, for example, someone was asking, you know, we update and, you know, let's say only one node get updated successfully and 2 other nodes not get updated, then, you know, now we return fail to the user, but somehow we have to correct the node we already updated. So that one have the latest time, but you know, we want to that node to go back to the previous version.
So no, I mean, like, first thing I just want to make sure that we won't be using time to make sure that which is higher version.
Yeah, V1, V2, you know.
Yeah, logical. These are like logical versions, right?
Yeah.
Like they are not based on time. So each, I mean, like if there is a 2 nodes which so are you saying that 2 nodes use the same version to represent different data?
Okay, so previously we talked about one, we need a quorum with 3, right? And then
Yes,
write to that node. We only successfully write to one node, right? The other node we cannot, so we return fail to the user. But, you know, at some time we want to keep our data consistent. So, you know, the data we write to one single node now becomes stale data.
Yeah, so there I think what I meant is like if your quorum is, it depends on the whether you are using strict quorum or floppy quorum. If you are using a strict quorum, it means that like out of 3 nodes, if you are writing only to one node, and the other 2 nodes, I mean like all the, I mean like the total is 5, right? All the other 4 failed, which means that your write request is failed. So you can discard this write which was successful in the node itself. So you'll need to worry about correcting only when you are storing this data in some of the other nodes. If you use a sloppy quorum, there are some other nodes which accept the data and then hand off the data later when these nodes come back again. Sorry, I erased that quorum picture. So there is never a scenario like you are failing the request and then you are storing that stale data. So that stale data exists only when there is a successful write, but the other 2 fail nodes in the out of total 5, 3 successfully wrote, the other 2 are out of sync, or they may be in sync. That we will get to know when we compare the Merkle trees. So this Merkle trees ensures that whichever the remaining 2 nodes of the successful write quorum, if they were out of date, then they will be updated using this anti-entropy process of using Merkle trees.
Okay.
If I made it clear.
But at that time, 3 have the latest, version, right? 3 will be like V2, the other 2 will be V1, and we want to roll back, to V1.
So, are you saying that 3 nodes access successfully and 2 nodes were failed?
Yeah.
Is this the scenario you are saying?
Yes.
So, in the 3 nodes which were successful, so if our version was V2, and in this fail nodes, say if our version was V1, then if one of the Merkle tree is this and other Merkle tree is this, then we get a mismatch. If we pick the Merkle trees of 2 nodes which are both failed, then they both will be same because they both will have the V1. If you pick the Merkle tree of one of the successful nodes and one of the failed nodes, then this process ensures that the 2 fail, whichever the node that you are picking out of failed nodes will actually get updated when you compare the Merkle trees.
In this case, 1 node is success and 4 node is failure. If 1 node success, and then we write it to that node, right? And 4 node is failure. So it, we write, okay, we're unable to write. But somehow we have to roll back the value on the success node.
Oh, okay. Are you saying that now out of 3, you are able to only, so out of 5, you were supposed to accept right, but only 1 node responded success.
Yes.
And all of them failed.
Right.
So this 3 failed and the other 2 remaining also failed. So this is the scenario, right? We're talking.
Yes.
So if all the 4 failed and only 1 accepted success, then it is, if you are using a strict quorum, then this is a failed write. So you need to respond write was failed to the client. So you need to discard this successful write because you are telling the client that your write failed. So this synchronization you need to worry only when you are responding successful to the client. If it was a failure, you can simply discard the write on the node on which basically roll back the write on which one node it was successful because you are failed to reach the quorum.
Okay.
If you use a sloppy quorum, this data would have end up in some other nodes, but you would have responded success because some other 2 nodes would have stored the data that the coordinator will know, and whenever somebody is reading, they may read the stale data because you are using sloppy quorums. So, and till the time the other nodes which handed off took the data and they're waiting to hand off to this nodes, the clients may see stale data. And in the book, like designing data intensive systems, like most of the concepts which I'm talking is actually you can even read from the book. So I mean, like they even give a analogy like the sloppy Qurans. Like imagine like you forgot your or you lost your key to your house and you ask your neighbor to temporarily sit in their home, like till you find out or figure out where the key is, and then as soon as you found, like you get back to your home. Something like that. Temporarily you sit somewhere, some data is sitting somewhere, and come back to the same Quran. And this Merkle trees is kind of a background process to synchronize the data, to make sure that all the Qurans remain up to date. I think we are a little out of time. So any questions?
We're already 2 hours into the session.
Yeah, I think I'm done with the concepts wise because those are the two I wanted to cover and all the replications. Yeah, if you have any other questions, you can ping me in Slack.
I think the people in the chat just asked for the reference material, and I think these sessions are mostly like to give a overview, but more things we need to explore ourselves.
Yeah, I mean, like this is just to make you aware of the concepts. Now that if you have some idea about what this single leader, multi-leader, you can even browse any articles that you see about any of this leaderless or multi-leader, single leader replication methods, and you can see how it works. Now that you have understood most of the terms, like if you go and browse, or if you have the Designing Data Intensive Application by Martin Kleppmann. So that's a very good book. And if you go to the replication chapter, it is in detail. But if you haven't started reading, don't go straight into this replication chapter. So it's good to start from the foundations. So, or you can directly browse the articles in Google for these topics like single leader replication, multi-leader, like or the leaderless replication. You get tons of articles. I think if you read that also, you'll be clear. I mean, like at least like you can remember this.
Sure.
Okay. Hope the session was helpful. I'll stop recording now.
Sure.